So, Ms. Avantika, Charles law. Now, in Charles law, what we need to remember is that it's a relation between the temperature and volume. So, what will remain constant is pressure. Are we clear about this?
Yes.
See, again and again, we have these four variables. In gas laws, we have four variables. One is pressure, one is volume, one is temperature, one is the number of moles. Number of moles. So when we do gas laws, these are the four variables. Now in these four variables, we will be playing basically the gas laws. We will be playing on these four variables. So for example, last time we did Boyle's law. In Boyle's law, when we did Boyle's law, we kept the temperature constant. Now when we are doing Charles law, we'll be keeping the pressure constant. Are we clear? Then there'll be something called a gay-lussac law, in which we will be keeping the volume constant, and then finally we'll have a Avogadro's law. But what you need to remember in whenever you are studying gas laws is that the gas laws are a play on these four variables only. Are we clear on one thing?
Yeah.
Okay. So let us look at the simple definition of Charles law first. We'll look at the simple definition first, and then we'll look at the complicated definition. So the simple definition is very simple. That if I increase the temperature, if I increase the temperature, and if I have to keep the pressure constant, I'll repeat. If I increase the temperature, if I increase the temperature, and if I have to keep that pressure constant, if the temperature increases, the volume will increase. This is one thing. Is it making sense?
Yeah.
Very simple law. That if I take a piston and there is some gas in it, there is some gas in it. Now I have to keep the pressure inside this piston constant. The pressure should be constant. But
Mm.
then what I'll do is I will keep increasing the temperature. So for example, I have a Bunsen burner in which I provide heat to this gas. Now if I have to keep the pressure constant, of course the volume would expand. Am I clear?
Yes.
And because these are gas laws, so of course the material would always be gas. Now,
Mm.
again, what I was trying to tell you. So, if you look at these variables P, V, T, and N. Now,
Mm.
if you look closely, the pressure is constant. The number of moles are also constant. Why the number of moles are constant, Avantika? Because it is a closed piston. No gas has left the piston. Am I clear?
Yeah.
So that is why I am studying the relation between volume and temperature. And what I am saying is that when the temperature increases, the volume increases. Is it simple?
Yes.
Okay. Now let us start adding some complications to it. One is that the temperature which is being talked here, this temperature has to be always in Kelvin. It can't be in Celsius. Are we clear?
Yes.
Now this law that volume and temperature both are related to each other, volume and temperature both are related to each other, can be put in a mathematical form which looks something like this. I will show you the formula from the textbook. It can be put in this way that V1 upon T1 is equal to V2 upon T2. What is V1 and T1? So this would be state 1, this would be state 2. So this would be V1, this would be T1. This is state 1 and this would be state 2, V2, T2. And the relation is that V upon T is always constant. Are we clear, Vantika?
Yeah.
See, don't get confused about this V1, T1 part. It is pretty simple. All it says is that, so for example, this can be taken as V1 and this can be taken as T1. So this would be V2 and this would be T2. Any doubt?
No.
So the law is saying that V1 upon T1 is equal to V2 upon T2 when the pressure is constant and the number of moles of the gas are constant. Are we clear one thing?
Yeah.
Of course, 2 upon 300 is equal to 4 upon 600. Have you understood?
Yeah.
It would be 1 upon 150. Both of these are equivalent fractions and they are equal to 1 upon 150. Are we clear?
Yeah.
So this is the simple definition of Charles law. And then slowly we will start adding some complication to it. The first complication that we have added is that the temperature that is being mentioned here, the temperature that is being mentioned here is called the Kelvin's temperature, and you need to remember this. Of course, this you have done in the lower classes also, but usually in lower classes, what they say is it is Celsius plus 273. But if you see, they have mentioned 273.15. Do you see this?
Yeah.
Okay. Now we will do few numericals to understand this. Once we have understood the gist of this law, then of course we will try to look at the complicated part of this law. But let us do these very simple numericals. Can you do this problem 10.2? शिवांग तेरे पास पेन पेंसिल है?
नहीं.
ठीक है. जब तक अवंतिका क्वेश्चन कर रही है तो अरेंज कर सकता है क्या पेन पेंसिल?
ठीक.
अवंतिका, यू कैन स्टार्ट. So Avantika, this is the first numerical, volume of a given mass. Now if you see, there'll be two kind of numericals. So in the first numerical, they will say volume of a given mass of a gas at 0 degree Celsius is 2 decimeter cube. Calculate the new volume of the gas at constant pressure when the temperature is increased by 10 degrees Celsius. So one thing that we need to understand is that if constant pressure is mentioned, then we know that this is a case of Charles law. Avantika, are we clear?
Yes.
Because in examination, now because we are doing Charles law, so we know that we are doing numericals of Charles law. But in examination, we won't be aware which numerical is this. Now compare this kind of numerical with this kind of numerical. A 20-liter container holds 0.65 mole of helium gas at 36 degrees Celsius. At a pressure of this, what will be the new pressure inside the container if the volume is reduced to 12 liter, temperature is increased to 1.25 mole of additional helium gas was added to it. Now when they say this, again we have P, V, T and N. Now if you see this numerical P, V, T, N, what you will observe is that the number of moles is constant, the pressure is also constant. So only these two are changing because only volume and temperature is increasing, changing. So we'll be applying Charles law. Avatika, have you understood?
Yeah.
But in this case, if you see, this is a case where 20 liter contains 0.65 mole at 37 degrees Celsius at a pressure of 6 to 8.3 bar. Now this is the state 1 and this state 1 will change to new pressure reduced to 12 liter. Temperature is increased to 177 and 0.125 1.25 mole is additional is added. So 0.65 plus 1.25 mole. Have you understood what I'm trying to say?
Yeah.
So here the state 1 is P1, V1, T1, N1 and the state 2 is P2, V2, T2, N2. So you need to be very clear when you are doing exam because in an exam they will give you all kind of numericals. So you won't be aware that which law is applicable. So you have to study the numerical very closely. Have you understood what I'm saying?
Yeah.
Then at times you will have to make some assumptions also. For example, if you see D part, hot air balloon has a volume of 2800 at 99 degrees Celsius. What is the volume if the air cools to 80 degrees Celsius? Now they are not saying anything about the pressure or the number of moles. But because no other information is given, I'll have to assume that Charles law would be applicable here. Have you understood what I've said?
Yeah.
Because कुछ और है ही नहीं. अगर कुछ और है ही नहीं तो मैं फिर कैसे न्यूमेरिकल करूं? Because they are saying nothing about the pressure and number of moles. Because they are saying nothing about it, I'll assume that these two are constant. Have you understood what I've said? See, right now we are doing numericals of Charles law. So we understand that in numerical C, numerical D, numerical E, 0 degrees Celsius, gas occupies 22.4 liter. How much hot gas Celsius Kelvin to reach volume? We understand that the Charles law V1 upon T1 is equal to V2 upon T2. This would be applicable. We understand that this. But when we are sitting in exam, we won't be aware that which law would be applicable. And that is why you will have to, look at the numerical very closely. That what are the conditions? What are the conditions which are changing? शिवी तुझे समझ आ रहा?
जी.
The second thing that you will always have to keep in mind is whenever you are doing gas law numericals, never do the numerical in terms of just make it a habit that always convert the degree Celsius to Kelvin. Have you understood one thing?
Yeah.
This is a very simple thing that you can follow. Never ever do in gas laws. In gas laws, never ever do a numerical in degree Celsius. Never ever. Always convert it into Kelvin.
Yeah.
See, gas law is a very simple chapter connected to thermodynamics. Thermodynamics at times becomes a bit difficult, but gas laws is very simple. Gas law, people who find gas law difficult are the people who are facing difficulty in the stoichiometry part. जिनको मोल concept समझ नहीं आता उनके लिए gas law थोड़ा सा difficult हो जाता है. Otherwise, it is a very simple concept. Okay.
Okay.
After this introduction, let us try to see कि ये this numerical is simple enough. ये all these three numericals are simple enough. The only thing is कि what we need to understand is conversion हमें समझ आने चाहिए और कुछ बेसिक चीजें हैं कि we can't be applying टेम्परेचर जो है वो डिग्री सेल्सियस पे हमें नहीं चलाना. तो 0 डिग्री सेल्सियस, so this would be 273 Kelvin. 2 decimeter cube, 2 decimeter cube. This is state 1. Calculate the new volume of pressure if the temperature is increased by. Now, when they say by, you should understand that 0 degree Celsius would become 10 degree Celsius, 0 plus 10 degree Celsius. So 10 degree Celsius would be 283 Kelvin. And they are asking us the new volume. So V1 upon T1 is equal to V2 upon T2. Something, are we clear?
Yes.
So this would be the A part. And in B part, V1 upon T1 would be V2 upon T2. Here it is decreased by 10 degrees Celsius. So rather than basically this would be minus 10 degrees Celsius. And hence it would be 263 Kelvin. Are we clear, Avantika?
Yes, sir.
And when I solve for V2, of course, because on the left hand side, my volume is a decimeter cube. When I solve for V2 in part 1 and V2 in part 2, I will get my volume in decimeter cube. Are we clear?
Yes.
Did you get the right answer?
Yeah.
वैसे भी तेरा?
जी.
Okay. The numericals are simple. You won't face any difficulty in the numericals. So if we look at the D part, hot air balloon. So this is our V1. This is our 99 plus 273. 372 Kelvin. What is the volume if the air cools to 80 degree Celsius? So this would be 273 plus 80, 353 Kelvin. So again, V1 upon T1. V1 upon T1. T1 is 372 is equal to V2 upon T2. T2 is 353. And again, my answer would come as a meter cube. Ms. Avantika, did you get the right answer?
Yeah.
Shivang, tera?
जी.
Okay. Let us look at the E part. At 0 degree Celsius. So 273 Kelvin. Gas occupies 22.4 liter. So this is my volume. How much hot must be the gas in Celsius and Kelvin to reach a volume of 25 liters? So again, V1 upon T1. So V1 upon T1 is equal to V2. Now here V2 is given upon T2. This is what is required, and the answer which will come here would be in terms of Kelvin. Why? Because I have taken Kelvin here. So this is all that simple things that you need to take in mind. That so, for example, here the volume is in liters, and on right hand side also it is in liters. But if on left hand and right hand side, if the volume is say meter cube, on one side it is meter cube, other side it is decimeter cube, then you should know how to convert between meter cube and decimeter cube. Mr. Vantika, am I making sense?
Yes.
So Simple numericals. And last time also we had done this, and just note this. Just note this conversion. You would have noted this, but just keep this in mind. This conversion at times becomes very confusing for volume also and for pressure also. Are we clear till here?
Yes, sir.
So, so this is simple Charles law. If you want to see a small animation also, so if they ask an exam what is Charles law, what we should write is that because at times they will ask you the definition also in school exams, not in usually in competitions. So for school exams, at constant pressure, the volume of a fixed mass of a gas is directly proportional to the temperature in Kelvin. Now these are the three things that you need to understand. One, the pressure is constant. Two, we are talking only of fixed mass of gas. The mass of the gas is not changing. And the third important thing, the temperature is in Kelvin. Can you see that? Is Avantika, are we clear?
Yeah.
Okay. Now there's a small animation. I found it at one of the websites. Do you see this animation?
Yeah.
What they are saying is that the pressure, if you see these weights on the piston, these weights on the piston are basically the constant pressure. So if you see the pressure has been maintained constant, and I'm heating the gas. When I'm heating the gas, the temperature is increasing. When the temperature increases, the volume also increases. Are we clear?
Yes, sir.
वैसे भी तुझे समझ आया?
जी
And usually again in school exams they might ask you. See, these are the kind of things that they usually ask in school exams. So, for example, they might ask you that list out various real life examples of Charles law. Now, in Charles law, you can give very simple examples. So, I'll try to explain this helium balloon thing with you. So, it says that if you have chance to go on a chilly day, you might have noticed that the balloon crumbles. However, if you take the balloon to a warm room, it regains its shape. Have you understood, Avantika, what he's trying to say?
Yeah.
So, for example, in colder countries, if you take this helium balloon, you are inside the room. The balloon would have the same shape. So, say it would have a shape like this when you are inside the room. But when you take it outside, when it is chilly outside, this helium balloon will sort of crumble. Is it making sense, Avantika?
Yeah.
See, the pressure is the same because the atmospheric pressure is the same. the the number of moles of helium in the balloon is also constant. But what has changed is the temperature. The temperature inside would be more. Let us assume inside the temperature is say 25 degrees Celsius. But when you go outside, the temperature changes to say 0 degrees Celsius because we are talking about a cold country. So here, if you see, the temperature has reduced drastically, and consequently, the volume also decreases. Are we clear, Avantika?
Yeah.
So at times they might ask you a question based on real life examples of Charles law. So again, this is a beautiful example. Actually, that is what they were trying to do when they found all these laws. So hot air balloon. So hot air balloon. If you have ever observed, there is a burning flame here. Have you ever seen a hot air balloon? This is one thing
Yeah.
on TV. So when the temperature increases, the volume increases. Now, you know how this works is if you see any of these documentaries, etc. So, for example, this is the ground. So these balloons, they are just lying on this ground, and then they start the flame. They start the flame. Now, as they start the flame, this balloon starts to expand. It takes a shape like this. Have you understood one thing?
Yes, sir.
Because the volume has increased, the mass of the gas has remained the same. Mass is same. So therefore, density would decrease. Is it making sense? Because density is mass per unit volume. The volume has
Yeah.
increased, but the mass has remained the same. Therefore, density
Mm.
would decrease. Because density has decreased, as per buoyancy, as per buoyancy, now this balloon will start to rise up. Is it making sense?
Yeah.
It is just like you will see, you know, So, for example, the bucket in your bathroom, you take your mug, the plastic mug, and invert it and try to push it inside the water. It will always try to rise up. Why? Because the density inside is low. So, similarly, so any lighter object, basically, any lighter object will always try to go up in a medium whose density of air is more than density of gas or air in this balloon. Is it making sense?
Yes.
In very simple terms, if it is getting confusing, warm air rises up. Rises up. Why? Because its density of warm air is lesser than density of colder air. Am I making sense of something?
Yes.
So these are the sort of real life examples of Charles law. I will send you this page. You can have these two examples are there. Third example you can take like this. So you know if you have a tennis ball which gets crumpled, one of its side gets dented, just place it in a warm water. It will regain its shape. Similarly, they have taken an example of from a colder country that most of you might have observed that basketball when left outside on a cold winter night shrinks in size. Again, the example of Charles law. Am I making sense of one thing?
Yes.
So now we will try to understand this graph of Charles law. More or less, I'll just take 5-10 minutes to finish this. So one thing that you need to observe is that at 0 degrees Celsius, the let us take a gas. Let us take a simple example of helium gas. So imagine some helium gas which is there in a balloon. Helium gas which is there in balloon. So at 0 degrees Celsius, it would have some volume. Are we clear on one thing?
Yes.
Okay. So the when this law was introduced, when this law was introduced, this is how it was presented. And here it becomes a bit technical, but let us try to understand. Their experiment showed that for a given mass of a gas at constant pressure, so the mass is constant, the pressure is constant, the volume increases with increase in temperature. It was found that for every degree that for an increase of every degree of temperature, so basically for every 1 degree rise in temperature, the volume of gas increases by 1273.15 degree of its original volume at 0 degrees Celsius. So let us try to understand this. At 0 degrees Celsius, your helium gas has a certain volume. Now, when I increase the temperature by 1 degree Celsius, the volume will become whatever the volume was at 0 degrees Celsius plus 1273.15 of the volume at 0 degrees Celsius. You guys are making sense or not?
Yes.
Let us increase the temperature by 1 degree more. So let me now make the temperature to be 2 degrees Celsius. So the temperature would be V naught plus 1273.15. Because now I have changed the temperature by 2 degrees Celsius, I will have a 2 here. Is it making sense, Avantika?
Yeah.
So at any temperature T degrees Celsius, at any T degrees Celsius, the volume of the gas would be equal to the volume of the gas at 0 degrees Celsius plus 1 upon 273.15 of multiplied by V naught multiplied by T. And this is written as Vt is equal to V naught plus T upon 273.15 V naught. Vt is equal to V naught 273.15 plus T upon 273.15, and this is what is defined as the 273.15 plus T is what is defined as the temperature in Kelvin. Avantika, am I making sense or not?
Yeah.
See, this part is a bit confusing, and that is why I wanted to do this at the end of the lecture. So this part is a bit confusing, but I will send you this particular page. Try to study this page if you want to understand. Only this part is confusing. बाकी सारा चार्ज ला बहुत सिंपल है. ये जो पार्ट है ना, ये थोड़ा सा जो यहाँ पर लिखा हुआ है, ये थोड़ा सा confusing है यहाँ तक. Have you understood, Avantika?
Yeah.
And this is the graphical representation. Basically, the graphical representation में एक चीज आपको सिर्फ ये याद करनी पड़ेगी कि you can note down this word कि these are, ये जो लाइन है इसमें प्रेशर कांस्टेंट है, ये जो लाइन है इसमें प्रेशर कांस्टेंट है. These are called isobars. Just note this word, isobars. So as the temperature is increasing, the volume is increasing, and this is called the absolute zero. This is called the absolute zero. Temperature less than absolute zeros. This is called absolute temperature, absolute zero. Temperature less than minus 273.15 is not possible. So, Avantika, are we clear?
Yeah.
So you'll have to read a bit about. I will send you these two pages. Again, you'll have to spend some time, just 5 minutes, about reading about absolute zero temperature, isobar, absolute zero isobar. So a bit of theory from this part, and this part. That is it. And next time when we meet, we will do this Avogadro's law, and we will also finish this PV ideal gas equation. PV is equal to nRT. Are we clear?
Yes.
So basically now in gas laws, what we need to cover is Avogadro's law, the ideal gas equation, PV is equal to nRT, and this combined gas law, P1 V1 upon T1 is equal to P2 V2 upon T2. This we can do in one lecture. And then we'll spend one lecture in this Dalton's law of partial pressure. And then there is a modification of the ideal gas. So this is the modification of the ideal gas. So about 3 more chapters would be required. And then once we have covered this, 3 to 4 lectures would be required. Once we have covered this gas laws, then we'll move on to thermodynamics. Are we clear?
Yeah.
Okay.